So good morning. Welcome to Krishna's classroom. We have completed the proof of one part of the theorem. Now what we are going to do is to take up the remaining part. The inverse function theorem statement is in the nutshell given here. I'll just read it out. E is an open subset of Rn. F is a map from E to Rn. F is a C1 map, and for A belonging to E, F dash A is assumed to be invertible. Then there exists an open set U contained in E, A belonging to U, and Fu open in Rn. So one of the things that you have to prove is that F of U is open in Rn. And this we have proved. Along with that, we have also proved that F is a one-to-one map of U onto V. Up to this we have proved. That is, we have already shown that F is a one-to-one map of U onto V. And Fu is open in R. This is what we have proved. Now, so the point is this: you have E, A, it's an open neighborhood of that. This is Rn. This is Fa. There's a neighborhood V, and what we are asserting is that F is one-to-one onto, and the only assumption that we made is this: F dash A is invertible. Incidentally, you know that F dash A belongs to LR. It's a linear transformation on R. We are assuming that this is an invertible linear transformation. And we also assume that F belongs to C1E. That means F dash, because F dash can be looked upon as a map from E into LR. And you have the norm here, you have the norm here. Here it's the norm of Rn, here is the norm of the bounded linear operators on Rn. And with respect to this, the induced topologies, we are assuming that F prime is a continuous function. That means F is a C1 function on E. That is the assumption that we have made. Then what we have proved is that the existence of U and V as Fu. We have proved that F is a one-to-one onto map of U onto V, and Fu is an open subset of Rn. Now this is what we have proved. Now we start looking at the other statements. So one of the statements that we are going to take up first is that F derivative of x is invertible So you recall the definition of U. What was the definition of U? The definition of U was that, okay. where let us recall what A is. A denotes f derivative of A. Second point is that twice lambda into norm of A inverse, because A is invertible, is equal to 1. This is how lambda is fixed. That is a choice that we have made. Or norm of A inverse to lambda. So now we recall one of the early results that we have proved. So recall let omega be the set of all invertible linear operators then what we assert is the following. Let B belong to such that norm of A inverse less than 1. Now you know that A inverse is a bounded linear transformation on Rn. Therefore, norm of this is finite, etc. So that we have already fixed what it is. Norm of A inverse is taken as 1 by 2 lambda in our specific case that we are considering. But this is a very general theorem. B belong to omega. Further, the inversion map I from see the latest statement that I is, that is the inversion map, is a continuous map we will have to use later. But for this part, I think we will, for the time being, work with it. So what do you have? So you know that, okay, take B equal to for an x. Then what do you have? You have for every x belonging to U, norm of which is equal to b minus a is less than lambda. Or I will put it this way. Norm of less than lambda. Then what can you say about this? See, lambda is, by definition, it is equal to 1 upon therefore and which is certainly less than 1. Therefore, the conditions of this theorem are valid, and which implies B is fix x, take this. Now this is true for, since the choice of x in U is arbitrary and all these conditions are satisfied, that f derivative of x is invertible for every x belonging to U. Now that completes the proof of this statement. U. So there is a correction there, it is U, not U. Okay. Now what we want to assert is this. So I am sorry for the mistake in the statement. The statement has to be read as x belonging to U. Okay, right. Now we shall return to this particular result later, but we need to use this property of the inversion map towards the end of the proof. But let me prove the other part. Now we are going to talk about the inverse of f. Let then y belongs to V. For x belonging to U, V. And choose K such that K plus or y plus K belongs to V. Then there exists some Z belonging to U such that Z is equal to f of Z equal to y plus k. Choose H such that therefore we have now the following estimates. Now we want to see, what we want to prove is that we prove that k goes to 0 implies this is the crucial result that we want to prove first. For that, so we make an observation. So what is the observation? The observation is that H is equal to G y plus k minus gy. Okay. Now let us bring in the phi map. Introduced earlier. Now phi works on U to U. So let us compute this, the effect of the phi map. See, we have fix some, not this one. So, okay. We have phi of x plus k equal to x plus k A inverse into y minus this is the phi map, and for x this is what you have, phi of x is equal to x plus therefore we will estimate this phi of x plus k minus phi of x, this is equal to, sorry, I think here it is x plus h. Okay, right. So this is equal to x plus h minus which is equal to h minus now what is this? This is essentially k, which is equal to minus. So this is the first estimate that we make. Therefore, we will take the norm of this. Norm of this is equal to norm of as I said in the beginning that we are using two types of norm. One is the norm in Rn, the other one is a norm in Lrn. Now I am using the same notation, but one should understand from the context what exactly we mean by that notation. So I am just recalling that or just reminding you of this. Now this is equal to this, and you know that this is less than, we have shown that this is a contraction, phi is a contraction with the constant coming as half. So we are invoking that result. Which we have proved in the first part of the proof. Okay. Therefore, we get norm of h minus norm of A inverse of k is less than half of norm of h. From which you can immediately conclude that norm of is greater than norm of h. So this is something that we shall make use of. And this in turn tells you that, and we can have an estimate of this. Therefore, you have norm of h, we can connect it with k because we know the norm of A inverse. This is less than twice norm of A inverse norm of k. And norm of A inverse we already know because we have had some kind of estimation earlier. What is that? Some estimate that we have used earlier. So you see that this is less than 2 divided by 2 lambda norm of h. Because I believe this is what we had. We had, lambda equal to 1 by 2 norm inverse, norm A inverse. So you have to estimate that norm of norm of A inverse is equal to 1 by 2 lambda. Okay. Okay, so what do you get from here? Therefore, so we get 1 by 2 twice this, so you get this. Therefore, this is equal to no, sorry, I think I should write here K. Right. Therefore, now we have got the estimate. The estimate is that norm K is greater than lambda times norm H. Therefore, or norm H is less than 1 by lambda norm K. So, therefore, it follows that as K tends to 0, H also tends to 0. So this estimate that's what we wanted to prove. Now what we do is, we have already seen that for x belonging to U, f derivative of is invertible. So we denote by T inverse. Okay, now let us start working on this. So we will try to estimate this. What we guess at this stage is that the derivative of g at y is going to be given by t if it exists. So let us find out. So we investigate. G is differentiable. us start with that investigation. Now we write, so we have to look at this. So G now we make use of our guess that we have defined T to be f prime x inverse. You know that this exists. Okay. So we guess that this is likely to be the derivative of G. So let us investigate that. Estimate this. Now this, you can easily see that this is x. Now T of k, k is what? K we have computed somewhere here. Okay. So this is equal to okay, let us write minus tk, and then this we write as, see, we have x plus h yeah, so we have to write h minus tk. This we write, oh no, sorry, I think tk. Now we will write this, therefore this is equal to now let us take T out, then what happens? This is equal to minus T inverse H. Okay, and that's equal to T of minus T of k is what? K is by definition f of x, that is y plus k minus y, and minus T inverse h. But what is that? T inverse h is equal to f prime of x. So we will use that. We have the estimate for this. Norm of g y plus k minus gy is less than or equal to norm of t divided by lambda into norm of h. K we are replacing by this inequality that we have just now derived into norm of f of I will write this h here. Now let then h tends to 0, which implies, see, the limit of this is what? This goes to 0, because we are assuming, okay, we want to show that this goes to 0, and so limit k tends to 0 of norm of g y plus k minus g y minus tk is less than or equal to norm of t, and this part is the derivative of, this part goes to 0. So this is equal to 0 since limit h tending to 0 of norm of equal to 0. That's the argument. Okay, therefore, which implies, see, here we have used the fact that for x belonging to u, f dash f is differentiable. Okay, that earlier statement that, and this is invertible, we have used that. So what you have is this one. Therefore, what do we get? We get g derivative of h, y exists and is equal to t. Okay, that's the conclusion. That's a conclusion that we make, which is equal to inverse. That's a conclusion that we make. So g is differentiable at y and the derivative is given by t. Okay. Now what do we want? So we want to go one step further. So we have proved the existence of g derivative. Now it is sufficient to prove, to conclude g derivative is continuous. That means g belongs to okay, so what we want to say is, I'll write it, rewrite it. To conclude that g belongs to CD, it is enough to show that G prime continuous, and therefore since y is arbitrary, it follows that everywhere on V this course. So let us work with this. So let us observe what it is. See, g derivative of y is equal to g derivative at f of x. And this is equal to T inverse inverse. This is what you have. Okay. So let us work this. So what is g derivative of y? G derivative of is equal to f prime of gy inverse. Now let us write this back. Let us investigate this map. Now this means the following. Okay, let us see what this means. See, y belongs to V. So y is mapped to gy, which belongs to U. Then what about f derivative at? So f derivative maps gy to omega. Omega is the set of all say this is the scenario. You have V, you have U, you have omega, copy of omega. So we take y, gy maps it here to f of x. Now what you have is that f derivative of x maps, see, f(x) to x. So f prime maps this x to some element. Now what do you do? You apply the inversion map. Then what you get? You get f prime of x inverse, which is equal to T inverse. Therefore, this is exactly the okay. G prime of therefore you see that G prime is from V to omega and G prime can be written as can be conceived as this is what you have called G, okay, G composition F prime composition inversion map. Okay, so what do we have? Let us investigate this. What do we know? We know that G is differentiable. Therefore, this is a continuous map. And what about F prime? F prime is a continuous map. Okay, and I is again a continuous map because F prime is continuous because we are given the data that F is a C1 map. So G is a continuous map. V. Then what about F prime? F prime. Sorry, not I feel this. F prime or F is a E and hence on U, which implies F prime is a continuous map on U. So you reach omega. Further, inversion map I is I maps F prime of X to F prime of X inverse is continuous on omega. So combining these facts, we conclude G prime equal to the inverse map composition F prime composition that is G is Here of course we have verified that it is just this property at a point y. Since the choice of y is arbitrary, we conclude that the whole thing is valid on the entire v, and from there we come to this conclusion. So this completes the proof of the theorem. Okay, let us just recap what all things we got. See, we had this f prime of x is invertible for every x belonging to u. We use that. Then we estimated what exactly is the derivative of g, and we concluded that, so note, remark, we have proved that g prime of y inverse where y is equal to this is the conclusion that we have. So we have actually got the expression for g derivative. Okay, so this completes the proof of the theorem. Okay, now we want to make one remark, another remark. We have used the C1 property f in the final step. Before that we have not used it. This is just an observation that worth making. So to conclude that G is C1, we are making use of this property, and that happens here. Okay, that happens here, right? We wanted to use the continuity of this f prime, that is x to f prime x. This particular map is continuous. That means f is C1, and that is where we have used it. Okay, so that completes the proof of this. Now, one of the immediate consequences of this theorem is the following. Get another result. So that actually completes the proof of the inversion mapping theorem. It's very worthwhile looking at. Now I have left out a discussion on the fixed point, the use of the fixed point theorem, which we shall do independently, because I didn't want the main proof to be interrupted by discussion on the map phi that we have used, because that merits a detailed discussion. It is worthwhile to know such maps, and that we shall do after completing the proof of the theorem. Okay, so let me just give a theorem, the following theorem. Is an immediate consequence of the inversion inverse mapping theorem. So let me make the statement. The statement of the theorem is F is invertible for every x belonging to V, f of w open for every open set Now this tells that all open sets in E are mapped to open sets in Rn by F, provided F is a C1 mapping of E into Rn and F prime, that is F derivative, is an invertible operator. Okay, these are the two conditions at all points on E. Okay, so this is called open of this is the, therefore if you want to prove that all open sets gets mapped to open sets, then you can take help of this inverse function theorem. Okay, and the power of this theorem would immediately tell you that all open sets are mapped under F to open sets. Okay, now this is quite easy to prove, because what we are essentially doing is this: you have E here and this is Rn. Now what you are taking is some W here, which is open, assumed to be open, and then it's enough to prove that Fw is open. You arbitrarily chosen W. And you know, we can gear it back to the application of the previous theorem or the proof of the previous theorem, because we are assuming F is C1 on E. That means, and we also prove that, not only that, we are assuming this. This is the assumption that we are making. So F prime x is invertible for every x on FW. So we can use that and then show that the FW that you get is a open set. What you do is you choose some point, pull it back here, and then take a neighborhood of that, and that an open neighborhood of that, then you can show that there is some open set which gets its one-to-one and onto, and the connections are established using the proof of the previous theorem. Okay, so that completes the proof of this particular part. So I just wanted to make some remarks on that, and that's quite easy to, you can, the details are left to you for an as an exercise. So we can make one more remark. Note that F is locally one-to-one. That is, locally on some neighborhood it is invertible. Okay, so you have U and V and the inverse exists. That's what we do. However, it is not possible F is one-to-one. Now we shall discuss some examples in our next lecture along with the nature of the phi map to highlight this point. At that time I will return back to this remark and then give some examples to make a point of this. Okay, so thank you very much. We will conclude here today.